Maximin rule. This is the first decision rule that I talk about. The rule is quite straightforward. Mathematically, you could state it as the argument maximum over all i's, and for the minimum of all j's for Rij, which is the mathematical expression that you'd see up there. In simple terms, what we're trying to do is we try to minimize the reward over all states for a given action. Then, for all actions, we find the action that maximizes the minimums that we actually have. Here, the i's correspond to states or state indices, and the j's would correspond to the i's would correspond, according to my definition, the i's would correspond to action indices and the j's would correspond to state indices. So if you want to follow this video, you might have to watch the state action model first to understand what I'm talking about. So I'm going to assume we have a set of actions, we have a set of states, and we'd like to find an optimal decision. Going to expand the rule using an example. Consider a bakery store where the cost to make a cookie is 50 cents. The sale price of a cookie is $1.50. The bakery sells cookies by the dozen only, and on any given day a maximum of 5 dozen cookies can be sold. The baker, however, chooses to make up to a maximum of 4 dozen cookies to be on the safe side. Now, given the circumstances, the objective is to find the optimal decision for the amount of cookies the baker should make per day, in dozens, of course. So, based on the problem, if it costs 50 cents to make a cookie, the cost of a dozen cookies, the manufacturing cost, would be $6. The revenue generated from a dozen cookies would be $9. Now, how did I get this? It's just 50 cents times 12 cookies per dozen, you'd get 6. $1.50 times 12 cookies per dozen, you would get 9. Now, there are 4 actions. The actions are A1, A2, A3, and A4. What it means is A1 would mean, or I could write it in a more generic way, AI would mean that the baker chooses to make I dozen cookies on any given day. And the states are S1, S2, S3, S4, and S5. So SJ would mean the bakery sells J dozen cookies. And let's also assume that the states are equiprobable. If you don't make this assumption, then we have to account for the probability of a particular state occurring, and that could actually make this problem more complicated. So we're going to assume that the states are equiprobable. So if we want to make an optimal decision, the first thing that we have to do is to come up with a reward matrix. So I'll go ahead and create the reward matrix. The reward matrix in this case is 4 by 5 because we have 4 actions and 5 states, And we actually have a reward function. The reward function is a function of I and j, simply written as r sub ij. The function is big R of I comma j, and I'm going to write it as r sub ij. So if you think about it, if the number of dozens of cookies made is less than or equal to the number of dozens of cookies that you're expected to sell. In other words, I is less than or equal to j, or in another way, j is greater than or equal to I. They mean one and the same. So if that is the case, then no matter what j is, no matter what j is, I could only sell I dozen cookies because that's all I have. For instance, if the customer orders 5 dozen cookies but you have only 3 to sell, the best you can do is 3 dozen cookies. So in this case, the reward function r I j would simply reduce to 3 times I, while 3 is the profit you make per dozen. Which is $9 minus $6, which would give you $3. The other case is when j is less than I. You make so much cookies, but at the end of the day, you don't sell as many. Then, in that case, Rij would be dependent on both I as well as j. So we get to sell j cookies, but we only made I. So the profit for j dozen cookies is $9 per dozen, so it is 9 times j. And the profit or the manufacturing cost for a dozen cookies is nothing but $6 per dozen, so you'd have 9j minus 6i. Now, if you come up with this function, you can actually get the previous function that we have by setting I equals j. If I and j are one and the same, then you'd have 9i minus 6i equals 3i. No matter what j is, you can only sell I amounts, so this condition, j greater than or equal to I, would actually reduce down to j equals I, always. So if you use this reward function, if we identify the reward function properly for our problem, we can complete the reward matrix. And the reward matrix could be written as follows. So those are my states, and these are those are my actions, and these are my states. So let's take the first case. J and I are the same, therefore you'd have to use the first function that we have because I and j are the same. So 3 times I is 1, which would give me 3. Now j is bigger than I, but even if a customer orders 2 dozen cookies, but if you have only 1 dozen made, the best you can sell is 1 dozen. So once again, we'd make use of the first function. So 3 times I is still 3. So it should be the same from here on out. Now, for the second action, I is 2, but j is 1. J is less than I, so we have to use the second function. So if you plug I and j in the second reward function, you'd find 9 minus 6 times 2, 12. You would get negative 3. Now, I is equal to j for that particular cell. In other words, you manufactured 2 dozen cookies and you sold 2 dozen cookies, so we'd make use of the first piece of the reward function. So 3 times 2 would be 6. For any state, 3, 4 and 5 dozens requested by the customer, you could only sell 2 dozens because that's all you have. Therefore, from that point onward, it is just 6, 6 and 6. Carrying on, if the reward matrix action is 3 and the state is 1, j is less than I, so we'd have to make use of the second definition of the reward function. When plugging in j as 1 and I as 3, we would get 9 minus 18, which is negative 9. And when you plug in j as 2 and I as 3, you would get 18 minus 18, you would get 0. Then you plug in the i's and the j's are the same, so you have to plug it in the first page, so you just get 9, 9 and 9. In the last scenario, I is 4, j is 1 in the first cell, and since I is greater than j, we have to make use of the second piece, so we'd have 9 minus 24, that would give me negative 15. Over here, when I plug in I as 4 and j as 2, I would get 18 minus 24, which is negative 6. And I proceed further, I would be 4 and j would be 3, so 27 minus 18 would be, it is 27 minus 24, you would actually get 3. In the next cell, I and j are 1 and the same, so we make use of the top equation and we fill it in as 12 and 12 from that on. So that is my reward matrix, and if I want to come up with an optimal decision, I'm going to make use of the reward matrix. So each value here is nothing but Rij in my original equation. So in this particular case, to be more precise, that would correspond to R11, and that would correspond to R55 and so forth. That is R45 and so forth. Now, the rule states that the optimal decision would correspond to the argmax of I, the minimum over all j, Rij. So what does that mean is I fix a value for I and I identify the minimum reward that I can get for each I. So in my previous table, I had 4 possible actions, A1, A2, A3 and A4. Now for each of them, I'm going to find minimum of the rewards, and I'm going to call this as R1, R2, R3 and R4. So how do I find the minimum? It's quite straightforward. So if I fix the first action, what is the minimum? If I fix the first action, it means I'm going to fix the first row. I'll have to find the minimum of all these values. The minimum of 5 3s is just a 3. So the first minimum is a 3. The second minimum is the minimum of negative 3 and all 6s, which is obtained by fixing the second action. So the minimum of the second row is negative 3. If I carry forward, I'd find that the minimum of the second row is negative 3, the minimum of the third row is negative 9, and the minimum of the last row is negative 15. So I'd end up getting negative 3, negative 9 and negative 15. So that's the first part of the puzzle. The second part is to find the argmax, the argument maximum of I over all the rewards we just found, minimum j or ij. In other words, we have to find the argument maximum of I over R1, R2, R3, R4. So what is the maximum of all these rewards? The maximum of all these rewards are 3 minus 3 minus 9 minus 15, and the maximum of that is just 3. But we're looking for the argument that resulted in the maximum. Therefore, the arg max of I would just be the action that resulted in this maximum. Therefore, that action would have an index of 1. Therefore, that index is just 1. So this tells me that the optimal decision in this case is to impose the optimal decision is to use action 1, which is the baker makes only 1 dozen cookies. Now, the expected reward in this case is $3. Now, you can actually see the disadvantage of this approach. In a very simplistic sense, this approach would let the baker to miss out on opportunities. In other words, that suppose the customer orders 2 dozen cookies, he actually would not have 2 dozen cookies. He only has 1 dozen cookies because that is the action he's choosing as the optimal decision. So although the optimal decision is 1, this particular optimal decision would actually result in loss sometimes, and when I mean loss, I mean opportunity loss. In other words, you'd miss out on something for which you could have been prepared, but you actually did not prepare yourselves because you wanted to be on the safe side. This is the equivalent of underestimation in statistics. So what the baker is trying to do here is, I don't care how many dozens that I may get, dozens of cookies I may get as an order, but I'll just make 1 dozen cookies and sell that 1 dozen. Of course, you're guaranteed to have a $3 reward if you take this approach, but you would actually miss out on making, say, a $6 reward or a $9 reward, and reward is just profit. So although the Maximin rule is a great rule, sometimes it is not the best strategy. So I hope you understood Maximin rule. The next rule that's going to come is Maximax rule. Thank you for watching.